for today, I have a new distribution. Actually, I have two new distributions for today. But one is an old distribution that we're just going to give it a new name. So here's what I'd like you to think about. So we have learned about the normal distribution. We know that the normal distribution is created mathematically by a formula. It's got that natural log thing in it. And we know that the shape of the natural distribution, the shape of the normal distribution is mostly determined for us by two descriptive statistics. The mean, which tells us where it is on the number line, and the variance, which does what to the curve? So here we have a normal curve. If I increase the variance, what's going to happen to my curve? If I decrease the variance of my curve, it goes higher. Okay? So that's important, right? The shape of the curve is always the bell, but the variance tells us what the bell looks like, whether it's flat or narrow. In our normal distribution, we use this to represent the population. Today, we're going to learn about a distribution for when we take a sample. What's that look like? Let's call it a bucket. It's an upside down normal distribution. Because here's how we're going to think about this. I've got this distribution of all of these numbers. And what I'd like you to do is to take a handful out of my bucket. Just one. It's like Halloween rules. Okay. One handful. I don't want you in there like doing that. You've got some of my bucket. Like a piece of candy? Okay. She's got some. Your turn. Okay. Everybody can draw from my bucket. Here's the great thing, though. My normal distribution, as you draw from it, it's still full. No matter how much you draw from it, that bucket still has the same amount of pieces of candy in it. Okay. Now, each of you have drawn from my distribution. In your hand, you have a set of data. Right? One's a Kit Kat, one's a Butterfinger. If this is shoe sizes, then you've got a 13 and a 10 and a 4. Right? If this is test scores, you drew out 3 students. You've got a 95, 42, and a 77. Right? So the 3 of you each have some data in your hands, all drawn from the same bucket. Your sample mean of the 3 that you have in your hand, your sample mean of the 3 that you have in your hand, and your sample mean, they might all be different. If we take all of these various sample means, I'll let you all dip from my bucket. You should all have different sample means because you're drawing out different things, right? So again, if it's test scores, you're drawing out 3 different students than you're drawing out. Some of you might have the same students because remember, my bucket's magic and it refills, right? So her sample of 3 students could include you 3, and his sample of 3 students could include you 2 plus you now, because it's a refilling magical bucket. Okay. What we're going to get is if everybody did that, and everybody has their sample means, we're going to get a distribution of sample means. So our data now is your sample mean. So all of our data in here are all of these sample means drawn from each of your individual little samples. And that makes up the volume of our curve. Have I lost anybody yet? We're good? All right. This is the sampling distribution of the mean. I used to describe this as I'd have a cutout of the normal curve, and we know that there's a center point to it, right? The symmetry point where we fold it. What's that center point of the normal curve called? Starts with an M. The mean. Okay. And then I pull out from my pocket a second normal curve that's split up the middle. I set it right on top, kind of go together, like a car's U-joint. Actually, I had another term for it, but I got to stop saying that. All right. And it sits right on top at that point. And so at the point of the distribution's mean, turn it sideways. I got like a three-dimensional interlocking normal curves going on here. And that one there is the sampling distribution of the means. But I lost my things and couldn't find them this week because I moved offices. So you get the bucket instead. Here's a good example. I actually did this one day. So universities are great. They're fun. They got an energy to them. They've also got a bunch of weird people with PhDs walking around. You get a PhD by essentially not leaving school. Like if you just hang around long enough, they'll give you one and you'll go away. That's how I got mine. So people think it's because you're smart. No, it's just because you're not smart enough to find a job someplace else. So of this university with all these PhDs, if I were to tell you, according to the book, that the average age at which a person completes a PhD is 30 years old. Not too bad. Like if you went straight through, you graduate at 21, by the time you're 30, that's like 9 years. That didn't quite take me that long, but okay. Let's just say 30. Grad school's rough. A lot of mental health issues with grad school. And it has a standard deviation of 7. Where did these numbers come from? It doesn't matter to us. This is a math class. We're just trying to learn here. Let's not question the numbers. So if I were to draw a distribution with a mean of 30 and a standard deviation of 7, that's what it looks like. That's the curve. Now if I unleash you upon the world, that is Coastal Carolina University, and I tell you, come back next class with a sample mean age of PhDs. And we'll compare. And we'll see what we have here at Coastal. So I did this one day. I took my example and I'm like, I'll go collect some data. So the first 3 PhDs I ran into, all right, I was one of them. I was kind of lazy. It was me, Dr. Burler, and I think Dr. Smith. And I said, how old were you when you finished? And they're like, why do you want to know, creepy man? And the answer is, oh, I'm doing this thing in stats. I found this statistic, average is 30. I just want to see how we stack up. So I collected all the data of the 3 people plus myself, including myself. And my sample mean was 36 years old. A little off, okay? But 36 years old, so that's the red dot on the curve. That's the place for 36 years old. What is my expected sample mean? If I were a betting man, and I am, what number should I have guessed that I would have gotten in my sample? Why?
Because that's like what they consider the average, so you can expect your sample to
Yes. All right? Because if I'm randomly drawing from a distribution that is average, that it has an average of 30, then my random draw should be 30. That's the expectation. But I didn't. Mine was 36. So then that begs the question, how likely is it that I would get 36 years of age from my sample of 3 people when I know the answer should have been 30? If only we had a way to figure out probability under a curve and comparing a number we got versus the one we expected. Wouldn't that be interesting? If only we had a method to do that. Well, we do. It will require us to use the sampling distribution of the mean. It's just our normal curve. Almost. This is where he gets you. So modality, right? What's the most frequent outcome? Well, the mean of this sampling distribution of the means should be mu. So again, it's that interlocking, U-joint that I got going on. They should be at the same point, the two curves. In terms of symmetry, this distribution is approximately normal. Now, approximately is a word that in the English language means the opposite of what you think it means. Kind of like literally and figuratively. When you say something literally happened, it had to have happened, but most of the time you use it as it figuratively happened. Like, I literally died. Then you better be dead on the floor. And why are you talking to me, you zombie? Cut its head off. Approximately, people use that as a word that they think means precisely or exactly. At approximately 7:07 a.m. No, an approximation is a guess. So it approximates. It's kind of like a normal distribution. That's what approximately means. I'll tell you how we can get approximately more normal in a minute. In terms of variability, how do we discuss the variability? Well, again, we have a measure of that. But now when we think about our measure of variability, we're talking about the average distance from the mean. So now we're talking about the average distance of our average from the mean. And that gets really weird. Yes. So we're going to give it a new name. And we're going to call it the standard error of the mean. It's the standard error of the sample means. Right? All of the sample means. Right? So there's a amount of variance in our measure of variability because we're drawing from a sample. Now, perhaps, why did my sample of 3 suck? Like, I was supposed to get an answer of 30, but my answer was actually 36. Why might that have happened? Well, that's the result, right? My number was too high. But why was my number so high? Perhaps. How could I have done a better job? Yeah. I had a pretty small sample, right? My sample was 2, plus me figuring out how old I was when I got my PhD. Yeah. Right? I actually have to look on the wall at my PhD to remember when I got the thing. So my number actually could have been wrong. I don't know. My sample was pretty small because where does the population mean come from? The entire population, all of them. Where did my sample mean come from? Literally the first 3 PhDs I bumped into between this room and my office. I took the elevator up. My office was next to Ann's at the time, and John Smith was walking to the copier. And then I sat down in my office, and I added those 3 numbers together, and I had my slide. Not exactly a great sample. So again, I had the thing that I wasn't supposed to use anymore, the U-joint, the bucket. And then I found this online, and you know, if you squint and like light a candle and get a little bit of high, you can kind of see what I'm talking about here, right? right? How we have two curves. Again, this is a two-dimensional object representing 3 dimensions. Right? So if our x-axis is the regular distribution, you kind of see the lines. And then I tell you, well, on top of that, we've got another distribution. This is why we call it a bell. Because not only 2-dimensionally does it look like a bell, but also 3-dimensionally it looks like a bell. And you put 2 of them on top of each other. Don't let this give you nightmares. Okay. So why are we talking about all this? Why about the approximately? Why do we care about the sample size? I'll get to introduce another fun math thing for you. Bless you. There's this thing called the central limit theorem. And it has to pertain to exactly the problem that we're facing. A theorem is an idea. It's not quite a law, but it's more than a hunch. Theorems are good, but they're not proven. And the central limit theorem tells us that as our samples get bigger, then the sample means that we draw from them will more approximate a normal distribution. So in terms of samples, the size of the sample matters. We need to pay attention to that. If you want a conventional rule because you're an undergrad and you like quick and fast rules, how many pages, how many sources? 30. But again, it's an approximation, right? It's not an exact number. As we approach 30, as we get closer to 30, the answer might actually be 33, but 30 is close enough. For us, that's a good cutoff between when we have a normal distribution of our sample means and when we have something else. You do this. Thanks. All right. So what do I mean? Let's do an example. Let's work through an example, and then I'll tell you why we need to use the other thing. So we like to experiment on children. There's a lot of them. They're squishy and flexible. We have them institutionalized for 8 hours a day. One of the things that we like to experiment on children is seeing if they learn and how to best maximize learning so that we don't have more stupid people out there in the world. So I can vouch for this. I have children. We experiment on our kids all the time, try to figure out what works. Let's say they're in school and they're taught a reading skills program, because that's why you send your kids to school, so your school can teach them how to read. The units that we commonly use is words correct per minute. As a parent, this is the worst thing you will face with your school, because your child will come home with a sheet of paper, and every night you have to time them for 1 minute to see how many words. And you would think they are in the Olympics, the amount of stress and anxiety that this causes them. It is awful. Abby has cried doing this. I'm pretty sure John's going to break some furniture when we have to do this with him next year. It's awful. But you read the passage, and then when the timer beeps, you put mark on the paper where they finished, and of course they count all the words for you, and so you do it that way. And you track their progress throughout the year. Sucks. 20 kids go through this program, and after the program, they read 150 words per minute. I think that's faster than I can read. I'm not sure if it's out loud or in your head. They estimate that in the population, children read with a mean of 124.81 and a standard deviation of 43. So you have this program, you test it out on 20 kids. Does it work? Give me the wrong answer first. Does it work? What's the simple, easy, wrong answer? Without even thinking, looking at that screen, tell me if the reading program works. You have no knowledge of statistics at all.
Yes.
It's obvious the reading program works. Why? How do we know it works?
Their average WCPM is higher than like the whole population's average.
Yeah, these kids are better at it. These 20 kids, we taught them up, and now they read 25 and a half words faster. Clearly the program works. Now, thinking of the subject of today's lecture, what are those 20 kids? They are a sample. They're the 3 people I bumped into between here and my office. They're your handful of candy from my refillable bucket. They're just 20 kids. How many kids are there? How many 4th graders are there? A lot. And we just picked 20. Now, if I'm trying to sell a school on buying my reading program, what 20 kids do you think I'm going to test? I'm going to go down to a GT class and be like, hey, GT critters, come here for a minute. Take this test. It'll only take a minute. Read. Okay, and put your hand on your ear. Just do it. It'll work. Trust me. You'll read faster. So there's 2 things. 1, I've picked out the best kids, and 2, I've given them a placebo effect. I've said, if you do this thing, you'll do something faster. Oh, okay. And they're all GT kids, like my daughter, so they're like, yay, positive reinforcement. I'll do that. Is that a representative sample of 20 kids? No. I mean, there are 20 of them, but they're not randomly drawn from the giant bucket of infinite number of 4th graders. Right? So I need to take into account the fact that I have a sample, that my 150.35 is derived from a sample. So if we're going to work through this, so the sample mean is 124.81. That's our null hypothesis, right? Our null hypothesis is if the reading program does not work, then our sample means should be equal to our population mean, because remember the U-joint, we're at the same spot. Our alternative hypothesis is that the reading program works, and that the sample mean of the students in the reading program should be different than the population mean. That's all we're saying, is that it's different. Make a decision about our null hypothesis. So we're going to talk about alpha. What probability do we have to find? How rare is it that we had a 25-point improvement when we expected there to be the same, right? Because we always work from the null hypothesis framework. We'll always start assuming that the null hypothesis is correct, and then we look for evidence in our sample that is different and that we can reject the null hypothesis. So we're going to set our alpha. Alpha is easy, 0.05. It's always 0.05. Then we're going to create a decision rule. At what point will we reject the null hypothesis in support of our alternative hypothesis? For us, in the social science, we do a two-tailed test. A two-tailed test. Why? Because we call these parts of the curve out here the tails, and there's 2 of them. In theory, we might believe that the reading program, our expectation is that it will do what to the students? Improve them. Does every treatment always result in improvement? No. What could happen instead? We could see a decline. Like, I could seriously jack those kids up. They might not know how to read after I talk to them. It's like you guys. You come in here and you're like, oh, I think I know what's going to happen. And then I start talking and you're like, I am so lost. I thought I knew this stuff, and then he did this thing with the line, and the next thing I know, like, the two curves are making out, and I don't know anything anymore. Right? So it could have a negative effect. So what we do is we take that 5% and we split it in half. So there's 2.5% over here, and there's 2.5% over here. The magical z-score that corresponds to having 0.0250 is 1.96. Magical number. Never forget that number as long as I live. Because if you do, you look it up on the normal distribution table and you go to 1.96, it is exactly 2.5%. And because we have two tails, that's our 5%. Oh, wait, what was this? This was 124.81. So what are we doing? Well, the center of this curve is mu. That's our population average of 124.81. Our sample mean that we got from the 20 kids was 150. I have to place 150 on this graph. In order to do that, I'm going to convert it to a z-score. If my z-score, this is my test, this is the moment, we're actually testing something, right? If that z-score is greater than 1.96, or conversely less than a negative 1.96, I can reject the null hypothesis and say that I believe the reading program matters. It has influenced the outcome. Why? Because I'm saying that my sample of 20 kids, right, that sample really is different than the expected outcome of the population mean. The observed versus the expected. So how are we going to do this? Well, our first real test. It's called the z-test for one mean. That's what it's called. The z-test for one mean, because we've got one mean. In order to calculate that z-score, z equals x minus mu divided by something. So before it was sigma. And that's what you did when I taught you this in chapter 5. Now, though, our sigma is a little bit different. This sigma is a measure of variance. Because we have to know in our curve the shape of the curve, right? So we have to know where we are relative, and z-scores are just sort of like miles per gallon. It's distance per standard deviation. Now we got something that's a little different. Because we're actually testing a sample mean. And what's really, really, really important about our sample means? The size of the sample. When I asked you, right, about my sample mean of 3 faculty, how can I get a better answer? You said, ask more faculty. So the amount that I'm wrong is going to change depending upon how big my sample is. So if that measure of variance there is like a measure of how much difference there is, there's going to be a lot more difference when my n is really small versus when it's really large. So I have to take that into account. I do that by swapping out the variance for something called the standard error. What the standard error does is it takes the variance that we have and then it takes into account our sample size. So the standard error of the mean is the population variance divided by the square root of n, where n is our sample size. Okay? So for this example, the variance in the population was 43 words per minute. But we can't expect to have the same variance in our sample because our sample is really small. So if we control for the sample size, we take the square root of n. An exponential shape gives greater effect at the lower numbers. So it says, basically, the reason we use an exponential shape instead of a straight line is that we believe the move from 2 to 3 observations is greater than the move from 33 to 34 observations. So the effect of it should be different. So by taking the square root, we're basically saying there's a greater effect at the smaller numbers. So if you think about it, like what's 3 squared? 9. What's 4 squared? 16. Right? The gap between 3 and 4 squared is actually 7 places. But the gap from 4 to 5 squared is actually 9 places, the gap between 16 and 25. And as you keep getting bigger and bigger, the gap gets bigger and bigger. Okay? By the actual number. Okay. Anyways. So this is our equation. We're going to have to convert the variance to the standard error to take into account the effect size of the sample. Square root of 20, because we asked 20 kids. Okay. We have converted our 43 variance to a standard error of 9. What happens when n gets bigger? What if n is 200? All right. So as n goes up, that value in the denominator also goes up. But the result to our fraction is that it gets smaller. Okay? So the larger your sample size, the smaller your standard error. Which is what we're trying to do, right? We're trying to have a small amount of error because of our sample size. Sample size is good. Bigger the better. So if we plug that into our equation, 150 words is our sample mean of the 20 kids we had them grab their ears, minus 124 of the population mean. That difference is 25.5. Divide that by our standard error, which is our size-adjusted variance, which is 9. Gives us a z-score of 2.64. Hot damn, I'm happy because what do I get to do? I got a z-score of 2.6. Yay! It is a pretty low percentage. That means I get to do what to the null hypothesis? Reject it, and then I can claim what? No, it is. It is. The null hypothesis says it's not helpful. The null hypothesis, no effect, null, niet. All right? If I get to reject the no, I get to say yes to the dress. Yay! This is the one. This is the explanation. Yay, me. Please buy my program. Okay. cautionary note. I've given you access to the General Social Survey, which has 64,000 observations for some of the variables. What's going to happen when you have a 64,000 N? Well, Dr. Wood, if I look at the equation, the square root of 64,000 is a lot. And when I have a fraction that has a lot in the denominator, that number is going to be the opposite of a lot, which is virtually nothing. And when I calculate the z-score, and my denominator is virtually nothing, what's my z-score going to be? A lot. So I'm going to warn you right now that somebody in this class is going to turn in a final paper, and they're going to have a z-score that is just amazing. It's 135, and it is going to be highly statistically significant, which, by the way, we don't do that. And I'm going to write, you made a big mistake. You got the right answer, but you designed your experiment, you designed your analysis so poorly that you could not have a difference that is not statistically significant. Yeah. So, if you want to reject a null hypothesis, just get yourself a huge-ass data set that has, like, 10,000 respondents in it, and then any difference from the mean, you can reject the null hypothesis. Yeah, got to be careful with that. And this is where when we talk about the analysis of big data, right, you will find differences, but it's about the size of the effects. That's really important. So what would we do? Well, our 2.64 is greater than our 1.96. How likely is it that we would, in our random sample from our distribution of all fourth graders, see that much of a difference if the program did not have an effect? It's actually less than 1%. So you can look up 2.64 in your table and get the actual probability number. Remember to double it because you have two tails. Okay. Quick digression on this. I don't like this idea that there are levels of significance. It either is or it isn't. I don't like stargazing. Like, either you reject the null hypothesis or you don't. And we call it stargazing because in some academic journals, they have different levels of statistical significance and they add more stars. So 0.05 is 1 star. 0.01 is 2 stars. 0.001 is 3 stars. I hate that. It's either significant or it's not. Because all I need to know is if you're going to reject the null hypothesis and say that you have evidence that your sample is different than what we would expect. This study revealed that teaching explicit systematic reading comprehension strategies to fourth graders is likely to increase reading comprehension skills. So if you teach the kids how to read, they read better. Okay. The conclusion, I don't like the way he does this, and I'll tell you why. The number of words correct per minute in a sample of 20 fourth grade students was significantly greater than the national normative sample of 124. He leaves out one word that actually changes the meaning of this sentence. It was statistically significantly different. What does that do? Well, I'm qualifying what the significance is about. We say that if you reject the null hypothesis, that is statistically significant result, which means that it's a low probability that you would observe this if, in fact, in the real world, there was no effect. If I tell you that something has a significant effect, on an object or a process, what does that mean? How much? Bigly. It's a fake Trump word. Right? Bigly. It would change bigly, like a lot. Like significant. I'd like to give you some money. How much money? A significant sum of money. And you're thinking, yay, money. Oh, I'm sorry, a statistically significant amount of money. All that means is it's different than zero. Right? Here's 10 cents. That is a statistically significant amount of money. Right? So we have to be careful. And I really need to change textbooks because I don't like this. But just insert a word and remember that when we talk about statistical significance, we're just saying the difference is more than zero. We believe there is a difference. It might be a little difference. It might be that, they read 25 words per minute more. Is 25 words per minute a lot? Maybe to a fourth grader. Sure. So I got 3 minutes to teach you something that was kind of the whole point of today's class. And I'm not going to do that today. So what I've given you is a new distribution for next class. It's called the T distribution. It's named after a student who is a guy that worked for Guinness. And I'll tell that story next class. But because I did not get through today's lecture, please do not do the section exercise for Chapter 7 because you will not pass it because you don't know how to read this thing. Okay? Now, for those of you who can't attend next week, I have already recorded a description of Students T. So if you really just don't want to wait till next week, you can go ahead and watch the video. Or if you just like the sound of my voice because it puts you to sleep, listen to that one. Okay? But I'll teach you this next week. Thanks.